In section 3.2, our goal is to be able to solve for missing sides using trigonometry. Our first example, we are just going to review how to set up and find the value of a trig ratio. So that means we are only setting it up for example 1. Okay, so we have tangent of theta. From my theta, I label the opposite, hypotenuse, and adjacent. From there, I use so, ka, toa. We are looking for tangent, so that means tangent of theta will equal the O side over the A side. And we are leaving it as a fraction because it only wants us to set up the ratio, and the ratio is our fraction. For question B, we label the opposite side O, hypotenuse, adjacent. And we're looking at our trig function, so, ka, toa. They want tangent. Tangent of our theta is equal to the opposite side over the adjacent side, and we leave it as a fraction. O, H, A. So, ka, toa. They want us to find cosine. Cosine of theta is equal to the A over the H. And we do not need to reduce, we're just going to leave it as 8 over 16. O, H, A. So, ka, toa. We need to find sine of theta. Starts with an S. Sine of theta would be the O over the H. And that is our trig ratio. Now, when they ask us to solve for the missing side, this is example 2. This is our new information that we have not done yet. So we are finding a missing side, round to the nearest tenth. That's one number after the decimal, if that helps, if you struggle. So tenth, one number after the decimal. So first step, I am going to try and set up an equation with a trig ratio. So I'm going to label, here's my angle, I'm going to label the opposite, the hypotenuse, and the adjacent. Now based off of that, so, ka, toa, I do not have an O. So I'm going to get rid of anything with an O in it. Then C is for cosine of my angle 32 equals the A side over the H side. Okay, and that is setting it up. We haven't solved it for the missing side yet. We've just set it up. So I'm going to set up all of my equations and then go back through and solve them. Okay, so we're just gonna review setting it up. And I'm just gonna go down. So O, H, A. So, Ka, Toa is my memorization tool. And it looks like H doesn't have a side, so I scribble out anything with an H, which means we're using tangent of our angle equal to the O over the A. Opposite, hypotenuse, adjacent. So, Ka, Toa. A does not have a variable or number by it, so A gets crossed off, which leaves us with the trig function sine of our angle equals the O side over the H side. All right, I'm going to set up the equations on the right now. Label O, H, A. So, Ka, Toa. O is missing. Scribble out anything with an O. C is for the cosine of my angle. 41 equals the A over the H. Opposite, hypotenuse, adjacent. So, Ka, Toa. H is missing. H's get scribbled out, which means we're using the trig function tangent of our angle equals the O side over the A side. O, H, A. So, Ka, Toa, and A is missing, so can't use anything with an A. Our trig function is starting with an S, which is sine of our angle equal to the O side over the H side. Okay, so this is what we did last time. Last time in class, we learned how to set up these equations. So hopefully that all looked familiar. Now, I'm going to go through and solve for x. This is the new step. If I want x alone and 4 is in the denominator, I'm just going to multiply by 4 on both sides, which will cancel out the 4 and leave x alone. Now, I can type this on my calculator. I'm just going to enter in 4. My trig function is the COS. COS, notice there's no little negative on it. It's just cosine of 32. I just type it in how it looks. If you want to, you can do 4 times and put the little dot. It's the exact same thing. Completely fine. So you can put it with or without the times. Whoops. So that gives us 3.39. 9 is going to bump this 3 up to a 4 to round it. 3.4, that's rounding it to the 10th. 3.4 is our x. Okay. So if I go to C, I get, look, I have 5 on the denominator. I'm going to times by 5. That leaves x by itself. 5 times tangent of 39. 4.04. 4 is too small to round the 0 up, so I'm just going to put 4.0 for my x. I have 3.9 in the denominator. I'm going to multiply by it. That cancels out and leaves x alone. 3.9 times sine of 61 is 3.4. 1 is not large enough to round the 4 up, so it stays 3.4. 3.4. Right. Now, on this left side, if you noticed, all of the numbers were on the denominator and x was on top. So this is how we solve for x when x is located on top. On the right side, x is in the denominator. So I'm going to multiply by x. So it's no longer in the denominator. And it's going to look a little weird at first, but so x is gone. And if I go to try and type this in, I can't type x on my calculator, right? Like over here I could type 4 cosine 32. I can't type x in. So in order to get x alone now, that I've moved it and it's no longer a fraction, I'm going to divide by cosine of 41. Divide by cosine of 41. That eliminates the cosine. X is alone and it's not on a fraction anymore, it's just x equals, and you're going to enter in 4 on top divided by cosine of 41. 5.3. So some of you might notice, instead of typing in 4 times cosine of 32, we're typing in 4 on top divided by our trig function. So let's try it again. This is the most difficult side to solve for. So I times by x, so I no longer have this fraction. That x is gone. Then I divide by tangent of 49 because I want x to be by itself. That eliminates, x is alone. So then I would enter in 2.4's on top divided by my trig function tangent of 49. 2.8 is going to round the 0 up to a 1. X is on the denominator. I want to get rid of that fraction. X is now gone, and now I want x to be alone. So I get rid of the sine 25. Sine 25 is gone. X equals 14's on top. Divide by the trig function sine of 25. That looks like a 23. I need to fix that. That is a 5. 25. 33.2 is not large enough to round that up, so it's 33.1 for our x value. On our last examples, these ones are just a little bit of a review. They are introducing a later module and just kind of reviewing Math 1. So as we look at our table, determine whether the given representation is linear, exponential, or neither. Classify each as such and justify your reasoning. Create a recursive and explicit equation to represent each table. Okay, so we have 2, and it goes to 3, then 5, and then 8. So if I'm looking for a pattern, it's going up 1, then up 2, then up 3, which means if I go to the next one, it'd be going up 4, up 5, right? I'm just going to continue the pattern. So 5, 6, 7, 8, 8, 9, 10, 11, 12, 12, 13, 14, 15, 16, 17 are my missing boxes. Now, you never did this freshman year. This is new, so we would call it neither. And later on, you're going to learn that this is called a quadratic. And we are going to have we're going to have a lot of units that cover quadratics this year. All right, this middle table, we have 64, 32, 16. Okay, looks like it's cutting it in half each time. Okay, so if I cut it in half again, half of 16 is 8, and then cut it in half again. 8 cut in half is 4. Whenever you're multiplying or dividing, it's exponential. And then we're going to write the recursive and the explicit. It's been a little while, so we'll see how well you remember these. So recursive means f of x. We write f of x equals f of x minus 1, and then I write my pattern at the end. So this will be the same every time for recursive, and then at the end I put it's timesing by a half. For the explicit, I can pick a number, so I'm just going to use 64, and it's cutting it in half each time, and then I put a power of x, and because I use 64, I have to say x is minus 1. If I had used like the 16, if I put 16 cut in half, x would have to be minus 3 in the power. Hopefully these are looking a little familiar. All right, next one. 10 to 26, adding 16. 26 to 42, adding 16. So it looks like we're just going to add 16 each time. 42 plus 16 is 58, plus 16 is 74. So if you wanted to check 10 plus 16, plus 16, plus 16, plus 16. Perfect. So when it does that, that is called a linear function. And for the recursive, and explicit. I'm going to find the 0. So if 1 is at 10 and I want 0, I'm going to go back one step. So I'm going to do 10 minus 16. 10 minus 16 is a negative 6 up here. Plus 16 is 10, plus 16, 26. Okay, so I want to have the 0. It'll help me with the explicit. So the recursive would be f of x equals f of x minus 1. And then at the end, you tag on the pattern. So my pattern is adding 16. For the explicit, I'm going to use slope-intercept form. My slope is adding 16 each time, so 16x. And my y-intercept is minus 6 at the end. Example 4, we're looking at tables. So they're giving us a table, 2, 3, 4, 5. It goes from 7 to 12. 7, 12 plus 5, 19, 9, that's adding 7, So 5, 6, 7, this would add 9. Is 28. Yep. Okay, so the numbers are changing. So that would be neither. We haven't learned about it yet, but this year you'll learn about it, which is called a quadratic. All right, this table. -5 to 5, that's adding 10. 5 to 19 is adding 14. And this one is adding, let's see, 19, 22. Okay, and let's check here. 2 to 7. That's a pretty big jump. So that's 5. And then 7 to 14 is a jump of 7. Okay, so 5 and 10. That means that, let's see, 10 divided by 5, that would make a 2. So that's adding 2 each step. 14 divided by 7 is adding 2 each step. And 22 divided by 11, that's adding 2 each step. So add 2 each step. The reason I know this is slope is y minus y over x minus x. So if I do y over x, it's the same as the 14 over, they all equal 2. So they all have the same slope each time. And because it's adding, it would be linear. So I'm going to write a recursive, which is f of x equals f of x minus 1, which we get bored of because it's just the same. And I put a plus 2 for my pattern. Explicit f of x equals, let's see, my y-intercept. I'm gonna go backwards. Okay, 2, 1, 0. So if I minus 2, that'd be -7. If I minus 2 again, that'd be -9. So I'd have 2x as my slope, adding 2 each time, and my y-intercept is -9. Example 5, we're given a graph. It is curving. This is called exponential. And if I have to make an equation for it, this is at 1, and then it's at 4, and then it's at 8. It looks like it's at 8. We're just gonna label these ones. Oh. One. Oh, okay. 1, 2, 4, 7, 8. That's interesting. Okay, so that one's exponential. This one makes like a U shape. That would be neither. You haven't learned about it yet, which will be called a quadratic. And if you had a graph where it looked like this, it would be called linear because it's a line. Example 6, we have 3x squared. This little squared power you have not learned about yet. It is a quadratic when it has that power of 2 as its highest power. Then right here we have the form mx plus b. This is a linear equation. And then we don't have an example of exponential, so I'm just going to write one. When you have a power of x, right? Power of x, that is when it is called exponential.